So for this session, we are pleased to have Professor Jeanie Lau from the Ohio State University. Professor Lau studied physics at the University of Chicago and earned her PhD from Harvard University in 2001. Before joining Ohio State in 2017, she was a professor at the University of California, Riverside from 2004 to 2017. Today she will be giving the two talks. The first is titled as Fabrication of High Quality 2D Materials and Heterostructures. Please join me in welcoming Professor Lau.
Hello, can you hear me? Yeah. Okay, yeah, thanks. Thanks for inviting me and having me here. So I'm currently at OSU, and so I just want to let you know that I did spend the summer here in Princeton about 30 years ago, when I was an undergraduate student doing one of the research experience for undergraduate. Okay, so since a lot has changed, I thought downtown became much bigger and nicer. So it's great to be back. And today, so the first talk will be fabricating van der Waals heterostructures. So I was happily agreed to give a talk at a workshop, and then later I was told I'm not going to only give one talk, but two talks. So I'm like, oh, what am I going to talk about? This is partly modified from a tutorial I gave at the APS March meeting. So that was, this is much more experimentally oriented talk, and the next talk I gave will be more about the physics we find. Okay. Okay. Anyway, so all right. So let's get going. Here. Okay. So just to say that, so the materials, right? So we are in the business of materials, condensed matter, but condensed matter. Well, do we start with materials? So this is, we just want to say that this. So materials, we start with. Very long time ago, right? So we start with the Stone Age, and then we go to the Bronze Age, and then we go to the Iron Age, and then we have the Industrial Revolution, right? So you can see that these well, this is not to scale really, but so every time we have a leap in technology, we start with the materials, right? And of course now, currently we have the age of silicon and plastics. And now, we are probably going to the quantum age. We're going to have the quantum information, quantum science and technology, and that starts with the quantum materials. So this is just a emerging quantum materials. So this is a bulletin that myself, Nian Xia, and Lin Chao have guest edited this issue back in 2020. What qualifies as quantum materials? Well, we can say that all materials are quantum in nature, because after all, they cannot exist without quantum mechanical interactions, band gaps, etc., right? Formation of gaps, band gaps, and everything starts with quantum. But some materials are more quantum than the others. So we come up with certain criteria to see what are they characterized by. So they're characterized by, for quantum materials, for example, they're characterized by the confinement, quantum confinement, reduced dimensionality, for example, one-dimensional, two-dimensional, or zero-dimensional materials, so nanotubes, 2D materials, quantum dots, for example. Nanoparticles. So they display emergent phenomena expected from single particles, for example, superconducting correlated states such as superconductivity, magnetism, ferroelectricity. So there's the important roles played by topology, and often there's non-charged degrees of freedom, such as Rayleigh degrees of freedom or spin degrees of freedom. I keep thinking wanting this to go forward, but okay. So 2D materials, I would say, certainly satisfy this definition, and they display usually at least two of these properties, sometimes all of them. Okay, and now 2D materials, starting with, as we know, starting with the starting with the graphene and now have expanded to include pretty much, I would say now hundreds of, say hundreds? Yeah, maybe at least tens of families, but there are literally thousands of layered materials, which we can try to isolate into monolayer field layers. So they include semiconductors, they include superconductors, they include charge density waves, they include magnets, ferroelectricity. Pretty much every single electronic state of matter has been observed in the monolayer limit. Okay, so now here's a brief history of 2D materials. So in the prehistory, they start with the study of monolayer graphite or metal surfaces. This is really, so at the time so I know there's probably some STM experts here. So when you want to study metal in STM chamber, sometimes a lot of times they find that the carbon atoms form this residual carbon atoms in the chamber form this they call it monolayer graphite, and this is considered very, very annoying because they want to study the metal. Now this monolayer graphite, so this is considered to be a nuisance at the time. Of course, one man's trash is another man's treasure.
What year was that?
Oh, this is I don't know, probably in the 80s. Yeah. So there's actually a bunch of study for 80s, 90s. They all think this is just annoying. So they don't really want to study monolayer graphite. They want to get rid of it. Right. So yeah. So So yes, feel free to ask me questions during the talk. Yeah, one man's trash is another man's treasure. So in 2004, there's isolation and transport studies of graphene on silicon oxide. This is by the Manchester group, Andrew Gaim and Kostya Novoselov have performed this study. And in 2005, so this back-to-back Nature paper from Philip Kim's group at Columbia and also from Manchester's group, they have shown that a so-called half-integer quantum Hall effect. It's not fractional quantum Hall effect, it's just that the conductance are quantized at, they call it half integer, at half a value of what you expect to be because of the, there is basically a offset in the conductance values. And so this is called a half integer quantum Hall effect. So in 2008, so the graphene was able to suspend, people were able to suspend graphene and to study its electrical, mechanical, and optical properties. In 2009, the fractional quantum Hall effect was first observed in graphene, and 2010. So the Nobel Prize was awarded to Graphene and Novoselov for their work on graphene. And this is also the same year where the HBN, hexagonal boron nitride, was found by the Columbia group to serve as a really great substrate. So usually, sometimes the Nobel Prize was given to a field that people say, oh, this is a kiss of death, actually, which means the field is mature, it's over, we'll move on. But turns out, I would say this is just really just the starting of some very exciting development in the field. So 2011, so I would say this is the first non-carbon 2D material was studied. This is by Andrea Key's group, so where they studied monolayer MOX2 as a 2D semiconductor. And in 2013, this is, I would say this is a great example, maybe one of the first example of van der Waals heterostructures, where they find this Hofstadter fractal spectrum in the graphene hexagonal boron nitride superlattices. This is also the same year where the Columbia group has found that you can actually make one-dimensional contact with two-dimensional stacks. And this is remains the most common method where we start to make the van der Waals heterostructures. In 2015, the superconductivity was found in monolayer or field layer transition metal dichitogenized by doping it to very high density using ionic liquid. In 2016, this tear and stack fabrication of twisted bilayer graphene was reported. This is from Tutu's group at UT Austin. And 2017, the magnetism and quantum spin Hall state was found in monolayers. So monolayer magnets found in chromium iodide and also FGT. And the quantum spin Hall state, this is the topological insulator state, was found in monolayer tungsten telluride. In 2018, now, of course, I would say this is the start of the twistronics, which enabled by this tear and stack fabrication of twisted bilayer graphene, where the more insulator and superconductivity in twisted bilayer graphene was, was discovered by Pablo's group at MIT, and that's the start of more electronics than twistronics. It's another field, which is still going very well right now, and up until now. And 2023, there was a first discovery of fractional quantum anomalous Hall effect, where you see the fractional quantum Hall effect, but zero magnetic field. This is twisted bilayer MOT2 by Sheldon Schu's group at the University of Washington, and also very quickly followed by the same phenomena seen by Longju's group in pentalayer rhombohedral stack graphene. Okay, so very brief history of 2D materials. I think there's many exciting developments. So that's really great. But you can see that every time, I would say, every time there's a breakthrough, it's actually preceded by some fabrication technique that enable the fabrication of very high quality materials that enable the discovery of the interesting phenomena and physics. Okay, so here's a brief outline of talk after this introduction. So we're going to tell you about the synthesis of fabrication techniques. Again, I was told this is this is the right level of of the talk. If you are experienced, feel free to fall asleep. Okay, I'll criticize. I'll say you did not sign my paper. That's okay. 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 So again, this is very quick survey of the field. So this is really broad field. So I try to just present some of the basics. Tell you about mobility, characterization improvement, and then so in the last half of the talk, I tell you about the effect of substrate on electronic properties on the correlated phases and band structure. So this is more or less focused on just the work from my own group. Okay, so how do we make the 2D materials? Roughly, you can divide it up into two big categories. One is so-called bottom-up synthesis, one is top-down synthesis, and then I will tell you there's also a combination of both bottom-up and top-down. So the first is the form we start with bottom-up, which is the chemical vapor deposition. This is so this is basically so called CVD. So this has been used for synthesized large-scale graphene or transition metal dichitogenized. So really what you have is just you basically put some catalyst, sometimes it may just be a metal, just something on the, this is just a whole metal on the surface of the substrate, or sometimes you start with an entire foil of metal, for example, copper, in the case of graphene, and then you pass some carbon-containing gas. In graphene's case, this is methane, for example, and so basically then the catalyst will help the formation of graphene on the surface. Sometimes, depending on the catalyst, it can be copper or it can be nickel. It can maybe give you monolayer. The idea is the copper will usually give you monolayer graphene because this reaction is self-limiting. And in nickel, it's harder to control the number of layers. So you might get regions with feel like two bilayer here, 3 layers here, 4 layers somewhere else. Okay, so this and there's actually a lot of also there's a huge field of study. So by controlling the conditions, and you can you can control, for example, the domain size and how the layers like the forms. So you can probably depend, for example, depends on starting substrate. Starting substrate is single crystalline, you have bigger domain size. And for graphene, if this is grown at vacuum, this is also will have more single crystal. But by and large, a lot of the, if you look at literature, a lot of films are polycrystalline. Okay, so you can, all right, so this is, so the kind of related method, well, we call chemical vapor transport, CVT. In this case, this is even easier. Usually you put just something, you put some crystals on one end of the furnace, so usually harder end, which kind of vaporize, and then they go transported by vapor to the cooler end, and they recondense to form, so it's sort of a dilute, it's diluted in the gas. So usually it condense to form a monolayer, a few layers, and usually the transport agent includes halogens, a halogen compound, and so this has been used, for example, actually this can be used to synthesize a large number of materials. So this yeah, okay, so the last one for bottom one is so-called molecular beam appetizing, MBE. So this type of crystalline substrate with multiple heat elemental sources. So they usually have this is ultra high vacuum, which so that the long mean-free path of atoms, so-called beam, therefore molecular beam, very fast shutters, very, very slow deposition rate, and so they have an appetizer group of crystalline films, and usually with atomically sharp transitions. Okay, so, all right, so what are the good thing about this bottom-up synthesis is that they can produce large-scale films, okay? So that's compatible with, for example, if you want to make any really real use of this of 2D materials, you really have to do something like this. Okay, you might want to improve the process, but I would say it's forced into one of these processes. And so what are the downside of this bottom-up synthesis is that a lot of the films are really kind of polycrystalline. It's difficult to control. I think it's very difficult to get a whole single crystal over an entire, for example, 8-inch wafer, or even over a 2-inch wafer. Okay, and sometimes depending on what you use, sometimes it's also non-uniformity in the film thicknesses. Okay, and I would say again, by and large, there's more defects and impurities in films obtained here. So I would say, by and large, films obtained in these techniques still pales in comparison in quality from what the next technique, which is top-down. Okay. So the top-down is in this case, well, there's I would say most, if you look at physics papers, where most most commonly used method is this mechanical exfoliation, which of course this is popularized by Manchester group. I don't know if I should want to say this was invented, because I was told also when I give one of these talks is that this actually using this cleaving technique is also not new. So it was a cleaving technique again by the STM group to produce atomically fresh surfaces and thin films. It's just that I think they not only use this to produce thin films, but what they see is that you can actually tell the film thickness from the color on the optical microscope. Okay, so this is basically you just start with a piece of bulk crystal, and then you take a piece of like Scotch tape, and you kind of fold this crystal many times so that it covers, so that because these are 2D materials, they cleave very easily. So every time you fold, you get some, you divide the crystal into halves of quarters or whatnot, and this gives. So you repeat this until this covers the entire tape, and then you sort of put the tape on the substrate, kind of rub it on, and kind of peel off the tape. Okay, this is very, very low tech, right? A very, very low tech technique. And this is especially compared with NDE, where you have $1 million equipment. This is you have a $2 Scotch tape. Okay, and then you can get for graphene, you can just call up one of the companies and say, one of the companies sell graphite, which I did. So I say, oh, can I have a sample? They say, yes, sure. How much do you want? I would say, well, how much can you give? I was thinking, okay, a little bit, right? They say, oh, I can give you a kilogram. So okay, so that's so that's this is at least in the beginning, this is extremely cost effective but very cheap method to produce monolayer films. Okay, so I think another thing that, but then you can also check the monolayer film by the color on the substrate. This, especially for conductors, it's actually pretty obvious. Well, obvious after you get some trained, after you got trained. For semiconductor, it's more difficult. This is just because of this interference of the light from the light reflecting off your 2D materials, and the one that goes through 2D materials and reflect off the substrate, and the substrate should be either 300 nanometers of silicon oxide, at least in this case, or 90 nanometers of silicon oxide, and so that this all this interference of light paths will have this, give you the best contrast for the of this your atomically thin layers. So in this case, for example, there's a monolayer, bilayer, trilayer. Anyway, so this is the monolayer graphene. I think it's a world record. We have this is my student obtained, which is exfoliated graphene. Well, he's so proud after he got this. He put his hair on the just on the same scale for comparison. Okay. Anyway, so you can determine the thickness by color contrast. This is very easiest, again, easiest, fastest way to do it. You can confirm it by atomic force microscope or Raman spectroscopy. I should also say that actually in this case, usually you will actually want to look at a green channel, the green channel difference. You can, for example, decompose the color into the RGBs in the different components of the color. Usually you will look at a green channel difference between on the flake of the substrate, and that actually sort of quantize and can give you a number of thicknesses. Okay, so all right, so the so for after you exfoliate, we exfoliate to when you get some films, then we use this to sample this van der Waals heterostructures. So this is selected material to form heterostructures, and this is really nice because many of these heterostructures are not possible. You want to do the conventional crystal synthesis, because when you try to grow one, for example, one crystal over another on top of another two different materials, they call it so-called heterojunctions. Those are usually confined. You are limited by many factors. For example, usually you need to have lattice match. The two materials should not, the lattice cannot differ by too much. Otherwise, you have a lot of strain, and you, of course, you have various chemicals may not be compatible, and all that. Right? So this basically this technique, you're not constrained by the same conditions as in bulk crystal synthesis. So we can create almost arbitrary heterostructure. So that's really nice about it. So what this does is that you basically, so this is, I would say, so there's actually a lot of dry transfer techniques developed. Again, I'm not citing everyone, but I would say this one is, was like one of the huge influence influencer in the field. It is by the Columbia group. So what they said, you first exfoliate materials on the silicon oxide substrates like HBN, for example, and then graphene, and you use your PDMS tape, PDMS polymer, so it's kind of sticky, and you use that to go down and touch the substrate. It turns out that you can use that pick up a piece of boron nitride in this case, and then you use the boron nitride to come in, and you can pick up graphene. Come in and pick up graphene. You can repeat the process. You can use this to pick up some MOS2, you can heterostructures. You can repeat the process as much as you like, limited by the graduate student patience, and error. Of course, the error rate goes up exponentially with how thick you want to go. Yes.
The PDMS is not sticky. How do you peel things off?
So that's a good question. So it turns out then at the end you drop down the whole thing on the substrate. You use heat, so it's actually thermal release. This is so use heat to heat up something 90 degrees, 100 degrees, 95 anyway, and then you kind of gently peel off. So it's the same thing that you do. For example, you have a sticker, or in your whole house, your home, you have a sticker on some piece of silverware or piece of something. Sometimes it's very hard to get off. I don't know if you tried it. You use a hair dryer to heat that sticker for a while, then it's much easier to peel off. The same idea, it's thermal release, because thermal release tape, okay. But the same idea as a heat to peel it off. Okay, and then so you get a stack, and this remains the same technique, technique with, I would say, many physics groups are used to make materials, because I would say the exfoliated materials and bulk crystals still have the highest quality, and so that's really great. You want to study new phenomena, new physics. I know Jane is probably giving the next talk, and I know Jane is, I think she'll go. I don't know if we're going to show some devices which have 13, a stack of 13 layers, which I would say which is heroic. Okay. Okay, so another thing is that what this work has shown is that it turns out you can make one-dimensional contact to 2D materials, so you etch. So the question is that if say you're interested in graphene, how do you contact it? So you can etch the, for the pattern you want, and then you can use reactive ion etching, and then deposit metal. So this forms can form an edge contact. So this is actually really great. Of course, there's now a lot of variety on this entire process. You can use different polymers, and then sometimes you can also don't need to do, if some materials the edge contact doesn't work that well, so you can also use the reactive ion etching to etch only the top layer of hexagonal boron nitride off. So this will you'll have to do a little bit of a study to figure out what, for example, HBN and maybe graphene, they have different reaction rate depending on what gas you use in the etching process. So you can partially have the top HBN off to expose the atomic layers. Okay, so I should also mention now there's actually a lot of push by the community to automate the process. Okay, I think that was first demonstrated by the Japanese group. I think also maybe a while ago, 2017 or 16. Okay, so but now I think there's a push to automate the process to build the automatic stacking bot. Okay, so that's so the idea is the idea is that you have something to automatically apply machine vision to automatically identify all the flakes and catalog them, and then you can have a robotic arm to come in and form the stack. Okay, but I think right now probably I would say probably that process, it can be made. Probably the best stacks are still made, unfortunately. Fortunately or unfortunately, depending on your perspective, it's still being made by humans. Okay, so I think lastly, I want to also just point out now there's also this push to combine uh, the two synthesis route, which is bottom up plus top down. So this is the work from Ji-Woon Park's group at the University of Chicago, where they have so they grow use MO, this molecular organic chemical vapor deposition, where now the gas instead of just some gas, so this is actually molecular organic compound as the precursor, which they come in. So this gave a very nice large area growth and with high quality, or relatively high quality. And they grow this, and then they have this they call it 4-dimensional stacking, which you have X, Y, Z control and rotation. And so they come in, they can use the PDMS film to pick up a so it's pre-patterned film. So pick up one film, and then you have the next layer. They can repeatedly picking up. I think they demonstrated 80 layers. So they can form this. So it's 25 layers here, and you can also have rotation control. And so this is, I would say, so this is a nice demonstration where you can have combining this top-down and bottom-up synthesis. Okay, so you can have, again, the deterministic synthesis of wafer scale. Okay, so maybe lastly about the fabrication part, of course, now there is a large number of marine materials. You probably also heard earlier of the talk. So where you overlay two atomic layers, you will form superlattice if they have a slight lattice mismatch, or you can have the same material with a small interlayer rotation. And so in the first case, you have you call it heterobilayer. In the second case, you call homobilayer. And so the period is roughly, so the superlattice has a period which is roughly the original lattice constant divided by either the lattice mismatch or the rotation angle. The angle has to be in radian, just so they know. Okay, so you can see that if the lattice mismatch or the angle is small, then you can have much larger period than the original lattice constant. And so you have, so for example, in the case of heterobilayers, I would say first example will be what I mentioned before, the house like the butterfly feature study in graphene hexagonal boron nitride. We have 1.8% lattice mismatch, and then a lot of various heterobilayers of transition metal ditrichalcogenides, so with various different lattice mismatch. And the homobilayer in this case, you have, of course, the most famous is twisted bilayer graphene. You can have now twisted trilayer, twisted 4 layers, twisted 5 layers. You can twist 2 bilayer graphene together. You can twist monolayer on bilayer, etc. And there's also, I would say, a lot of twisted MOT2, twisted WTSE2, etc. So that's what we've had so far. So a lot of interesting things in each case. Well, I guess this is supposed to be, so just tell you how, so that you have a superlattice forming. Okay, so twisted bilayer graphene, I think you heard a talk from Adam McDonald's group. I'm not going to tell you too much about it. This again, this is just when you have put graphene together, 2 cones next to each other, where they, where the 2 cones touch, they're going to hybridize to form different bands. And as you put them closer and closer together, the bands will separate. So the lower one is going to go down, the other one go up. At this major angle, this band is going to be really flat. So theoretically, the Fermi velocity should go to 0. Okay, and of course so it was first predicted back in 2011, and it's a lot of work done actually in this area. After that, of course, the first really the seminal paper from Pablo's group, right, really has shown that you can have really a lot of interesting correlated phases in there. And so how we fabricate this is so-called pair stack technique. Again, it was the first by Tutor's group in 2017. This was reported by them. So the question is, how do you, in this case, when you have twisted home bilayers, right? How do you make sure the rotation? How do you control the rotation angle? Well, theoretically you can start with two separate pieces, but that's difficult. You don't know what are the orientation, and also the angle here is so small, right? It's like what we want here is 1 degree roughly. And so how do you make that 1 degree rotation? So I think it's really clever technique from Tutor's group. Is that you start with one large piece of graphene, and you cut them in two. You use this pickup technique to, for example, to pick up one slice, the left slice, you rotate it by the angle you want, or maybe actually slightly different from the angle you want, because the angle will usually change. A lot of times they relax a little after you put it on, but for example, you rotate by 1.2, 1.3 degrees, you put it on the other one, okay, and then then you pick up the other one, and then pick up the bottom measure, and then drop it off the whole thing. Okay, it's like, okay, so this if you start from the same piece of graphene, this ensure you have exactly the same crystal orientation beforehand. And so this, then you can do your lithography and form the and your device. Okay, so next one I'm going to tell you how we characterize them, how we characterize the device once you have a device. Of course, you can characterize it by a variety of ways: Raman spectroscopy, scanning tunneling microscope, transmission microscope, atomic force microscope, etc. So in my lab, so I'm just going to focus on transport measurements. So I'm going to tell you this, how we characterize the transport measurement. So this is, in this case, we put after we forgot the layer, we put the source and drain electrode on, and then we have gate. So this is basically a field effect transistor configuration. So for the source, it just injects the electron. For the drain, the electron goes. And then importantly, we have a gate. Again, this is really, you don't have this control in bulk materials, because what the gate is controls the charge density on the surface of the material. For the bulk, since surface is really small part, very, very tiny part of everything that conducts, right? So that so for bulk, this really usually have no effect. Or very little effect, so you cannot see. But in 2D materials, they're all surfaces, right? So that's why this is a great technique. For 2D materials, what the gate is simply just a metal separated from your 2D materials by dielectric, which can be silicon oxide, can be HBN, can be some other oxides. And then this material and the gate forms a parallel plate capacitor. And so now that you can just by changing the gate voltage, you can change the charge density. Okay, so all right, so how here we have how do we characterize it? Usually we look at the number, we look at its mobility and mean free path. So this describes how good the metal is, how conductive your material is. So you can start with the Joule model, which well, this is pretty right. So with basic electrons, you know. These are the scatterers, which can be phonons, impurities, defects, etc. So the electrons go through them. They can scatter between them. And then you measure some resistance. So in the Joule model is given by the conductivity. So conductivity is the product of the charge density times the electron charge times the mobility. Again, this is like super simple undergraduate level. You want to just say mobility is base momentum realization time, the average time taken by the electrons between all the scatterers, okay, and divided by the effective mass of the electrons. And the mean free path is just Fermi velocity times the momentum relaxation Okay, so these, so if you have no scatter at all, the electrons can travel through without scattering, and then in this case you have a ballistic regime. Okay, so what affects mobility? So you can be intrinsic or extrinsic. Intrinsic meaning it's from the material itself. So you can have various defects, for example, vacancies, inclusions, substitutions, tune boundaries, etc., etc. So it depends a lot on how good the device, the material is itself. You can have domains, you can have stacking domains, you have more than one layer. You can twist angle if you're doing this twist bilayers. You can have and you can have crystallographic direct domains in this case. Okay, which is this is fairly common in particular in again the bottom-up synthesis in the CVD technique. And of course you have phonons. Okay, so then you have all the various phonons, acoustic phonons, longitudinal, etc., etc. And then in materials, you actually also have so-called CA phonons, which is the out-of plane, 2D materials out-of plane vibration, which actually turns out also is important in 2D materials. So extrinsic materials from the substrate or the environment, again, you have corrugations. For example, substrate, if it's not completely flat, then you have corrugations. And because 2D materials is so thin, they tend to conform to whatever, like valleys and peaks on the substrate. But even you think very tiny, if you have even the few ancient corrugation, the 2D material follow that, and that can give you can reduce mobility. Now, of course, you have charge impurities. Well, actually, I should say just any impurity of surface, but in particular, charge impurities plays a dominant role because they affect the transport not only right at the site where the impurity located, but because of Coulomb interaction, they actually can scatter electrons from far away. Okay. Of course, the substrate itself also has phonons, and so that can also reduce the mobility. Okay, so how do we measure? How do we define the mobility? So there's actually 3 different definitions, depending how you want to say. So you can have a Hall mobility, which is just, again, this is from the Joule equation. You just conductivity divided by the charge density. You can have field effect mobility. This is, again, for 2D material. So this one usually use this definition for anything, like bulk crystals, etc. Field effect mobility, this is basically tell you how effective the measurement is, how effective is with the, how responsive is to the gate. Like you use a gate to change charge density, how fast or how much does the conductivity change. So in this roughly, it's kind of a slope. You plot conductivity as a function of gate voltage is roughly the slope on this graph. And then you can also, another definition, so-called quantum mobility, which is 1 over the magnetic field at which quantum oscillation at first observed. And this should be in SI unit. Well, make sure the unit is right. So in this case, this is just some, this is actually just the data from my group. This is on 2D semiconductor. So you can see this is you plot resistance as a function of magnetic field. You can see that at some point oscillation, quantum oscillation starts. And so you can just look at this roughly, say, okay, it roughly starts here. And that's 3.3 Tesla. And so the quantum oscillation is 1 over, the field mobility is 1 over that. This is 0.3, but in units of meter square per volt second. But typically, when we say mobility, we use centimeter square per volt second. I don't know why, because it's larger number, I guess. So and this, so I would say this device has quantum mobility of about 3,000. And they are not always the same, all these numbers, because for example, part of the reason is that there's dependence in the scattering time on energy, so this two will be different, for example, and then especially in semiconductors, this also affected by you're also turning on from the band gap, you're turning from the band gap to the conduction band. Okay, so that's actually, so a lot of times field effect mobility will overestimate the semiconductors. If you just say that because there's also contribution from the slope to the slope, because you're also turning on the channel, okay, and that makes it look steeper than what it actually is. So semiconductor, just say you take you read the literature, the mobility value, take the a little grain of salt, okay. So these values can be very different. Quantum mobility tells you, how the electrons have to make several cyclotron orbits before they scatter. So that measures that. So they are not always the same. So a lot of times, I think, especially when you study quantum Hall effect, quantum mobility is what really important. Okay, so all right, so now let me tell you what are the mobility bottlenecks. And with example of graphene, here I'm plotting the graphene's mobility over time. So in the beginning, the graphene mobility is about 10,000 to 20,000. This is for first generation of devices on silicon oxide. So this is actually already pretty large value. If you look at the steel, this is larger than, I think, 99% of 2D semiconductors these days. Okay. I have to also say this value I quote at low temperature. Room temperature usually, because of scattering of phonons, you will be at least 1 order of magnitude smaller. Okay, so this so turns out silicon oxide is actually really not a great substrate because they have correlations, they have surface phonons. In particular, they have a lot of dangling bond or trapped charges because oxide it's a three-dimensional material, right? And so at the surface, the bonds are not heavy, and so they grab water, they grab something, anyway. So it's a lot of trapped charges at the surface, and that gave you charge impurities, and usually, so this limits mobility for graphene on silicon oxide to on the order of about 10,000. Sometimes they work really hard, you can get to 20,000, but that's about the limit. Okay, so this is the work from Furer's group, where they show that they actually intentionally deposit potassium, which is charged, which creates charge impurity on the surface, and show how this kind of mimics how some of the transport graphs you have seen in experiments. See that if you deposit more on the surfaces, will give you you can see the slope has changed, so mobility has decreased, and also this so-called charge neutrality point moves, which tells you how doped the surface is. Okay, so this is basically because this is sort of shows that the silicon oxide is really have a lot of charge impurities that will that limits mobility at low temperature graphene to about 10 or 20,000. So now, okay, so next stage is that silicon oxide is so bad, maybe we can just get rid of it. And so then let's suspend the samples. So we remove substrate altogether. So we have a lot of prior work in this area. So this is one of the devices which with graphene. This is an electrode, and we have a back gate and a top gate. So this is suspend the top gate over the graphene. And this also, well, you can suspend them. So let's remove the substrate. Then you can study the intrinsic mechanical, thermal, electronic properties. But actually, removing substrate also have another effect, because substrate is actually turns out to be important because it provides substrate provides screening. So removing substrate actually increases screening in the device. And so the third generation of device is the graphene of bicycle and boron nitride, which is just they also have a honeycomb structure with just the A and B sublattices, not by carbon, but one sublattice is boron, the other sublattice is nitrogen. So a layer by coming to flat, they have no dangling bonds or trapped charges, they're chemically inert, and have actually pretty large band gap with 6 electron volt. So this is really great insulator, and it's atomically flat, there's no trapped charges, And this is also popularized by Columbia Group, where they first shown the device, demonstrate the device. So in this case, okay, let's just say suspended device, mobility goes to a few hundred thousand. Okay, so few orders of magnitude improvement. And HBN uncharacterized device mobility goes above a million. In this case, actually, at this point, mobility stops being a good measurement because the devices are typically pretty small. Devices are probably 10 micron, 20 micron in size at most. And in this case, it's actually now it's limited by the sample size. Well, for something mobility this high, now people start quoting the mean free path. So mean free path, basically, you see reports of 30 microns, 100 microns. Okay, so it's so every time you have new fabrication technique, you have orders of magnitude improvement in mobility. Okay, so that's the graphene. How about 2D semiconductors? So you have like phosphor, TMPs, whatever, a lot of materials. Typically, mobility of 2D semiconductors tend to be a lot smaller. Quantum mobility, well, I would say limited to about 5,000. Field effect mobility, you can see kind of much larger, it's 100,000. Okay, so again, you can see a pretty large difference between the two. In this, I would say one reason is just that for 2D semiconductors, because they are binary compound, I would say actually because this entropy itself plays a role. Sometimes they tend to form, for example, they form clusters, right? The elemental clusters. So in this case, even just entropy itself makes so it's more prone to effects and whatnot. But this is still already pretty good. The silicon mobility is about on the order of 500 to 1,000. So the mobility bottleneck in this case, I would say, again, it's actually a lot of times it's you have extrinsic, which is substrate environment. Typically, I would say this is still important. If you read something in the literature, say they claim certain mobility values, say 50 or 100, when it's on the silicon oxide, then you make the same device of HBN. Typically, what we find is that you can expect about 10 to 20 improvement over the performance of silicon oxide. But I would say right now, still the bottleneck of the mobility of 2D semiconductors, a lot of it is the material itself. Your starting material has a starting with a really good bulk crystal, and then you can expect to find exfoliation. You can exfoliate the materials and have a higher quality. So I think there's a lot of work at improving the synthesis of the material, including synthesis of bulk crystals. Okay, so how to improve mobility further? As I mentioned, you have major source of scattering is charge impurities. So the charge impurities produce, you have Coulomb interaction, and so which is goes as 1 over the dielectric constant of the environment. So if you can increase dielectric constant, then you can reduce the effect. One of the things maybe you can try to use high K dielectrics, such as hafnium oxide. But of course, hafnium oxide being a bulk material itself, then they produce some mobility, some bad subtract charges. So if we want to stay with hexagonal boron nitride, what people has been using is that you put the graphite gate or some metal gate very close to the sample that improves the mobility. In this case, for example, within 10 or 20 nanometers, and so if that's close, that will screens the mobility on the order of that distance, screens the interaction on that distance, and so that can help further improves the mobility. So in this case, for example, you can have this type of behavior where you have the material you want to measure, then you have graphite top gate, graphite back gate, which is separated from the device by, say, 20 nanometers of H5 boron nitride. And then you actually have also silicon gate. And so that adjusting silicon gate can adjust the contact region that help you make better contact of the material. And you have top and back gate also help to screens the charge impurities. I think there's actually a recent preprint from Novoselov group, which they report when they put something like superclose, actually right at the level of graphene, they can see quantum Hall effect start at 5 millitesla, okay, which is actually amazing. Yeah. Of course, the caution flip side of that is that you want to see correlated states from the screening. Your screens is so much that maybe the correlated states might be suppressed. Okay, so there's a lot of things you need to play with that. Okay, any questions? How much time do I have?
2 minutes.
2 minutes.
20.
20. Okay. All right. So I'll tell you about this is effect of substrate, the lack thereof from field layer graphene. Okay. So in this case, I want the case studies with the tri-layer graphene, is in particular rhombohedrostack tri-layer graphene. So you may know that the graphite actually has 2 stacking. One is so-called Bernal stacking, which is ABA stacking. The other is called ABC or rhombohedrostacking. You can visualize them like this. So this is here we have bottom layer and the top and the middle layer. So in the middle layer, the one sublattice, which is blue, is exactly on top of the other sublattice, which is red. And then the middle layer's sublattice is in the middle of the hexagon or the bottom layer. Now you add the top layer. Okay, how do now you have 2 choices to add top layer. One is that the top layer and bottom layer exactly on top of each other, so that the sublattices are exactly on top of each other. That's the so-called ABA or Bernal stacking. Or you can shift them. No, well, I didn't shift it very well. Okay, I think slightly off. Or you can shift them so that the bottom layer and the middle layer and the top layer also form AB stacking, so that any of pairs of the 3 layers form AB stacking. Does that make sense? Okay, so so this is called ABC or rhombohedrostacking, and they can be distinguished using Raman spectroscopy. So in the tri-layer graphene, okay, the bands in this ABA stacking, the bands can be decomposed very simply into just if you have an odd number of layers, you can have 2 plus 2. You can have ABC, ABC, ABC. So then you have basically 2 plus 2 plus 2 plus 2 plus 1. Okay, so there will be odd number of layers, meaning you can, for example, in this case, your tri-layer, you have 1, so it's basically 2 plus 1. So you have 1 bilayer-like structure and a monolayer-like structure. So even if you have 5 layers, you have 2 bilayer-like and one monolayer-like structure, which is linear dispersion. If you have even number of layers, then you have 2 plus 2 plus 2. In this case, for example, in 4 layers, you can decompose into 2 bilayer-like bands. Okay. So this is ABA stacking. You have ABC stacking. In this case, so this is really interesting because it turns out dispersion goes roughly as the momentum to the nth power, where n is the number of layers. Okay, so bilayer is actually, you can see, so it's actually quadratic. Tri-layer graphene is cubic, and tetralayer graphene is quartic, and pentalayer graphene, which is now you probably all know about the exciting development, pentalayer graphene is going k to the 5th power. Okay, so you can see the bands get flatter and flatter, and when you have flat bands, you have a correlated states, which makes it interesting. So the way to understand it is, again, on the very, very time wavy level, it's just that all the stacked graphene So in this case, A2 or B1 and A3 and B2. So stacked graphene, they kind of hybridize to form higher energy bands. So they sort of forget about them, as long as you only carry. So they split the wave, for example, on the order of the interlayer tunneling, which is a fraction of EV. So if you're not working at on the energy scale of the EV, then you can forget about this electric transformation. We'll never worry about that. Okay, so then forget about all these bands. You're only left with the atom on the surfaces. Okay, so from A sublattice on bottom surface and B sublattice on top surface. And each hopping will give you one of these a power in this in the momentum. Okay, so that's why it gets flatter and flatter. So that's it's interesting. So I'm not going to tell you about this, but you probably already heard about this many times before. So there's a recently four pentalayer in particular, I think now includes tetralayer and also 6-layer, hexalayer, of graphene, where they have seen unconventional superconductivity, integer and fractional quantum anomalous effect, pneumaticity, etc. There are also pockets of the superconductivity behaving differently. And so this is a really exciting area. I think this is one of the frontiers in this material. Okay, so I'm not, and these are all sandwiched between hexagonal boron nitride, sometimes with or without a monolayer of WSC2 in this case. Okay, so what I want to tell you about is suspenders. So actually, okay, so we have quite a number of work on ABC stacked graphene. This dates back to more than 12 years ago. So we suspend them. In this case, this is back in those days when where this is before the discovery of using hexagonal boron nitride substrate. So this is where we can make suspender samples, very high quality suspender samples. So it's actually very clean. I would say it's actually cleaner than boron nitride supported samples near the charge neutrality point. So intrinsic area, but of course it's mechanically fragile, and versus hexagonal boron nitride HBN encapsulated device. So okay. Okay, so how to fabricate a suspended device? So you have several ways again. You can pre-pattern a substrate on the substrate. You still make a trench on the substrate, and then you directly exfoliate transfer the 2D materials across the trench, and then you can either how to make contact. You can either have pre-patterned electrodes. If your material is clean, so you can make good contact with pre-patterned electrodes on the substrate, or you can deposit contact through shadow masks. So the nice thing about this is that compatible with most materials, with a very clean device, because we did not use any chemicals in the fabrication, so there's no chemical residues. The main thing is the difficulty is that making contact is not easy. I think for example, shadow mask, you have to line it pretty precisely to this. Okay, so and another way, the other way is that you start with a fabricating device on silicon oxide. You can actuate the outside using buffered HF with a vapor. You dry with a critical point dryer, and so this nice thing about this is device a little bit more controlled. It has high, can make different shapes, different. In this case, you're really only doing 2-terminal measurement. Well, depending how you pattern it, but so it's a shadow mask. It's hard to make the features very small. So shadow mask is usually limited to about half a micron. In this case, you can make the features. You can make so you have little bit more flexibility in the device geometry. flip side is that the device has to tolerate etching from hexagonal nitride. Okay, so third technique is you use bilayer. You can use the sacrificial layer, which is for example PMMA, or this is LOR bilayer, and the different lift-off exposure and lift-off conditions, so that you can deposit the materials and over sacrificial layer, and then remove the sacrificial layer later. The nice thing about this is compatible with most materials because it doesn't need acid etching. The flip side is that well, you have to do many. In this case, for example, three lithographies, and they use residue. Okay, so another thing. Okay, so this is what we have done. So most of the materials are done with the second technique. Well, since we're working graphene very stable, temperature stable. So we have what we do is we make this. The third technique. So we can make this kind of material, and then we also put a suspended top gate on top of it. Okay, so this is a paper about how we make this suspended top gate. And then we use acid to etch, and then dry in a critical point dryer. So what is critical point dryer? In case you don't know, this is basically it puts in the liquid carbon dioxide. And beyond the critical point, you can go from the liquid phase to the gas phase. And that's actually without actually going the phase boundary, and so that reduces surface tension while drying this. You can imagine usually you dry in the liquid, the surface tension from liquid will drag the thing down, and this is monolayer, bilayer thick, so this is very fragile. Okay, so it goes through this critical point dryer, it does not go through that the phase boundary, and so this allows us to this thing remains suspended. Okay, and then okay, since we do multiple lithographies, what happens is that we need to then you have a lot of chemical residues from all the resists. So what we do is we do the current annealing, which means we just we carefully ramp up the Gaussian bias and measure the current, and actually several times. And so this tell you back and forth until we see this kind of curving over. The current starts to saturate, and usually tell us it's a nice good point to stop. And I hope I can make a video. Okay, we actually image what happens, for example, when we pass a current through a piece of suspended graphene. Simply. Okay, I guess it's all right. The link is broken apparently. All right. So what happens is that this in situ imaging, that's the end. We pass a current. Okay. We can see it's basically see a kind of clean area appearing in the middle, and it kind of spreads to the towards the banks. Okay, it tells us it's kind of removing the residues from the lithography. Okay, so now, all right, so okay, that's a lot of work trying to make these devices, and then let me just say that there's so what do we see? So this is in a bilayer graphene, a few layer graphene at the direct point, because the bands are flat, so you have strong interactions. This gives broken symmetry states. So maybe let me just say that. Okay, we have how much time?
6 minutes.
What's that?
6 minutes.
6 minutes. Okay, well, I should stop at 11. Okay, let me just say that what we find is that in this suspended graphene, again at the charge neutrality point, is at a gap insulator state with a gap of about 2 millielectron volt. So and this gap state can be suppressed. Like if you go to so this looks like a gap from looks like a spectroscopy from the, for example, that measures the band gap state. So this gap insulating state can be suppressed if you apply an electric field of either polarity, electric field in this case is out of plane direction, and you have two gates. So the sum of the gates, so back and top gate, sum of the gates gave you the charge density. The difference of the gates gave you the out of plane electric field. Okay, so and in this case we have out of plane electric field gave a can suppress this intrinsic gap if you do not apply anything. If you do not apply bias, you do not, just tiny bias. Yeah, and do not apply electric field, do not apply a magnetic field. So this has an intrinsic insulating state of about 2 millivolts electron volt. And so when we go to tri-layer graphene, we find a similar phenomena. Again, a charge neutrality point, but this the gap now is 40 milli-electron volt, and this stays like killed by large density of electric field of in-plane magnetic field. We go to 4-layer graphene. Now this now it's 80, with same thing, the same thing, but larger gap, 80 milli-electron volt. What's this state? So this state we think is a layer anti-magnetic, anti-ferromagnetic state, which is basically the spins on the two layers in the 2 layers, which surface top layer and bottom layer are oppositely spin polarized, so that each layer has the same value, so there's valley polarized spin polarized on each layer. Okay, and then so this gave a gap insulating state, and so here just summarizes what we think happens in. Again, this is suspended field layers. It's a layer under ferromagnet. This is so you start with layer under ferromagnet state. You have more than bilayer. The middle layers are inert, and so you apply in-plane field. This will cancel the electrons. Eventually, you arrive at, you have strong enough in-plane field, you arrive at a ferromagnetic state where spins are kind of aligned with the in-plane field. You apply a large enough out-of-plane displacement field. This will give you this layer polarized state where the electrons reside on the top or the bottom layer. I want to say that it is similar to what Longju's group has seen at the charge neutrality point in pentalayer graphene of hexagonal boron nitride. So this makes sense because hexagonal boron nitride also has a screening because the dielectric constant is 4. So they have to go to a pentalayer graphene to see this state, where we can see that in suspended sample, we can see in bilayer graphene. Okay, but of course they have seen a lot of other really interesting states, such as fractional quantum novel solid effect. Sometimes we're like, why didn't you go to 5 layers? We stop at 4 layers because people told me there's nothing new. I cannot get funding for it. But of course it's not really that simple. It's just because that suspended samples will actually it does not sustain very high electric field or charge density because of the electrostatic pressure. This can break it. So we have to limit the electric field apply in suspended samples. Maybe let me skip this. We'll just say that we in suspended field layer graphene with DC intrinsic magnetism, so which disappears about 5 Kelvin, and but magnets also has been seen in supported field layer graphene. 1 minute. Okay, so let me also tell you that I'll go through relatively quickly about the effect of substrate of field layer graphene. In this case, they actually having substrate of this actually changes the field layer graphene, and hexagonal boron nitride, having hexagonal boron nitride actually also changes the band structure of field layer graphene. So you know, a lot of times we think in our mind that hexagonal boron nitride just inert and just sits there and provides a nice high mobility environment for the device, but it's actually really not that simple. In many cases, we can treat it like that, but just keep in mind that its pricing itself can change material properties. Okay, so let me just say that again, it's not inert. It's really nice. It has clean, large density range, can sustain high density and displacement field, but it's not enough. Okay, so how do we see that? This is, okay, so let me just say that this is a case study is using ABA stack trilayer graphene. In this case, you have monolayer plus, again, there's 2+1 model, you have monolayer like band structure and bilayer like band structure, which have different symmetry with respect to the middle layer. So this one have odd symmetry for in terms of mirror reflection. This is the even symmetry, and if you only include gamma, this is so-called this SWMC parameters. You only include the nearest neighbor hopping, the interlayer and intralayer hopping, gamma 0 and gamma 1. This is the span structure you get. But turns out you have a bunch of other hopping parameters, and so you will include, for example, gamma 2, which will give you a trigonal warping, which is hopping between A1 and B2, and you include gamma 4, and the gamma 2 and gamma 5 will give you a relative shift between monolayer and bilayer bands, and open up the band gap. And so after you include everything, this is span structure you get. Is that you open up a gap between the two structures, and also there's relative shift between the two, so that overall structure itself is gapless. So now that if you just look at the, so each of this band, this monolayer-like band and bilayer-like band will give you lambda levels in the magnetic field, and the monolayer-like band will give you monolayer-like lambda levels, which you'll see lambda levels like this, and bilayer band will give you which bilayer-like band. So and they cross. So now that the crossing points can tell you the hopping parameters. Okay, and so there are many crossing points between the two. So in this Landau band, and so you will just look at. So in principle, you can determine the hopping parameters from the crossing points. But okay, so now you just look at literature. What happens is that crossing the numbers are different, and then we came in, we did 9 different samples, we got 9 different values. So what's happening? Okay, this reminds me of the joke that will happen to put 10 economists in a room. You get 11 opinions. In this case, we put 7 or 8 physicists in the room. We got 16 different opinions. Okay, so what's happening? So we did a more systematic math study. We just, for example, check the crossing points, and we'll just do this crossing point. For example, the P is actually, this crossing point is actually largest variation. Here we have 2 different samples. One is aligned to brown nitride. This one is not. You can see alignment because of this secondary direct point coming up. Okay, and now we can see that actually turns out crossing point finds systematic dependence on the angle between graphene, hexagon, and brown nitride, even at large angle, even at 25 degrees Celsius, 25 degrees. So normally you say that's large angle, don't worry about it. But actually it turns out it does change the band structure. Okay, so we can, this is you're decreasing the, so at larger angle you have decreasing interaction between hexagon and brown nitride and trilayer graphene, and also, and so now you can argue that what happened is that we actually if you do suspended samples, then you can see something quite different. This point moves much farther away because there is no interaction. So you can even just having suspended samples, and you also look at the band or the Landau band. Suspended sample have, for example, exceedingly robust -2 state. And so a number of these things, you can just see the band structure in suspended samples, and the substrate support samples are actually qualitatively different. And substrate supported, HBM supported samples, the details of band structure actually depends on the angle between between the graphene and HBM, even at large angle. Okay, so let me just say that this is what happened. Okay, so lastly, I just want to say there's a recent work on the archive. It just said now if you put this on a high dielectric constant such as SDO, you put a device on there with thin HBM separating the two. This STO's dielectric constant can be changed by out of plane displacement field. And so now we have in situ tuning of the dielectric constant on the substrate, and that changes the screening, and we can see the superconductivity changes as we change the substrate. So, okay, so let's just tell you the substrate, it's interesting. You can probably want to have more thought going into the substrate. A lot of times you think substrate just enough, give you an environment to support your sample, but actually you can change a lot of things. And we can say it's good, or it's bad, it's a bug, it's a feature, but in any case, it's something we can try to control. Okay, so let me just say, okay, at the end, okay, I'm a little bit over, but this is the end. We think we can do a lot of things. We want to stack it, and we can twist, and we can so literally limitless opportunities in 2D materials. And let me just thank my collaborators. Thank you for attending my talk.
We can probably take one quick question if you have any. If not, let's thank the speaker again. And we're going to have a coffee break and be back at 11:20.